Hi everyone, welcome to another episode of Mr. Carlson's Lab. Today we're going to troubleshoot and repair a Tektronix Type 503 oscilloscope. Let's see what's wrong with it and let's get it working again. Let's get started. Here's the Tech 503 oscilloscope. Fantastic little scope. It's kind of the mini version of the larger ones like the 547 and the 531 and 535, all of that particular 500 series. This is like the little squished down version of it. It is really neat. The 503 is a relatively low bandwidth scope. I believe it tops at about 450 kilohertz, but we might be able to stretch that with the sweep magnifier here just a little bit. We might be able to see some faster signals. We'll try that out here in just a little while. So even though it is low bandwidth, it's excellent for XY display. If you want an XY display scope that's very accurate, accurate on the screen to the graticule, you definitely want one of these things kicking around. And you can find them for, a pretty decent price nowadays. So completely separate gain adjustments on both the vertical and horizontal section. You both have positive and negative inputs on the vertical and horizontal section, as everything an oscilloscope should have. Nice triggering section. It'll internally trigger, externally trigger off the line. You can light up the graticule on the front here, intensity focus, all the stuff that you need to have an oscilloscope. Something like this, honestly, is great for a lot of troubleshooting. Even though it's a low bandwidth scope, once you know how to use these things, you can test a lot of higher frequency equipment with it. It's all about the technique. So I'll get into more of that on this channel here. I've done some stuff on that in the past, but I'll get a little bit more in depth in the future here and show how you can take an oscilloscope like this, which you can probably pick up at most ham radio swap meets for $10 or $15, no kidding, and use it for effective troubleshooting. And not only that, it's got lots of nice tubes in there that'll keep you warm in the wintertime. So let's see what's on the side here. It's in pretty good condition. It could use some touch-up paint. I've yet to get some Tech touch-up paint. I haven't done that. I need to go get a tin of the stuff mixed up, and I can make these things look like brand new again. It has the usual abrasions from being slid in and out, beside other equipment, things like that. You can see here's a nice little abrasion on the side here. So on the back side, we have, it has the newer handle too. The older handles used to decay and fall apart. These ones here hold up over time very, very well. Nice solid handle. So when I have a really nice old Tech scope, and I've got a bunch of old wrecked Tech scopes with nice handles, I do a lot of handle swapping. So I'll put these nice newer, I guess you could say non-stitched type of handle onto them, and these last the duration. So 117 volts, line cord on the back, little nice line cord holder. So you know what? Let's plug this thing into a variac. Put this over here and get this thing going. All right, I'll get the variac and everything all set up, and I'll be right back. I have the Tech 503 plugged into the current limited isolation transformer and variac supply. So what I'll do is I'll turn the scope on. Nothing's on over there yet. And what I'll do, so I'll move you in just a little bit here so you can see this just a little bit better. The bulb's in the top maybe. Get it all in what's going on here. So pretty much there, okay. So now this is in current limit mode up here. And down here I haven't turned anything on yet, and the variac is right down. So what I'll do is I'll turn this on so we really have nothing going into the scope. So the bulbs are in line right now. So what I'm going to do here is turn this up about 3/4 of the way. And this is very heavily current limited by these bulbs right now. And they started out bright, and as you can see, they're going down just a little bit, which is a very good sign. So what I need to do is watch those bulbs. These are very dim at the top here. So I'm going to turn this up just a little bit because there's really not a whole lot of brightness. In the camera, that might look a little brighter than it actually is. So they're kind of a dim orange color over here. I'll move that up so you can see that just a little bit better. So they're kind of a dim orange color. And I'm going to let this sit with the scope for about 10 or 15 minutes just to make the capacitors comfortable inside this scope. I'll be right back. About 20 minutes has passed at this point. Now what I'm going to do is turn this right up to the top, which isn't much different. So these scopes, they pull quite a bit of current. So when I flip this through switch, it's going to bypass everything and give the scope full line. So what I'll do is I will move you down to the scope. And I wouldn't want you to miss any action here. So move this down here, And I'll back this out just a touch. All right, so everything's on, we're ready to go. So what I'm gonna do is I'm just gonna flip that switch and see what happens on the screen here. There we go. See, the graticule got nice and bright. Oh, I do see a dot, and it zipped off to one side. We're somewhat off to a good start. Look at that. There's a trace on it. That's actually looking pretty nice. Typical Tekscope type of trace, pencil thin. So on the camera, it's blowing out just a little bit. So cameras are very sensitive to this. So this is very dim on my end, but it looks pretty bright on the scope. I'm looking at it in the monitor. I can't hardly even see that, but on the camera, it's pretty visible. So as you can see, at least I can see on the camera, it's, as you can see, pencil thin, right? Bring it up to center line. Adjust the focus. You can see that's what many scopes look like, or like that. But as you can see with this, I can almost disguise the trace behind one of the little etched lines here. If I move this up or down, you can actually see it passing the line. Well, at least I can on my end anyways. So pencil thin trace, beautiful. So far so good. Give it just a bit more intensity. So that's about standard brightness. So I'll turn on one of my signal generators. It's just an audio signal generator. And now this scope here has got that earlier type of connector on it. Most modern scopes have BNCs on the front. This has got that BNC PL259 kind of deal. So I'll put the conversion on here, or I should say a PL259 SO239 kind of deal. So this converts that to a BNC. Standard fittings you find on the back of ham radios and CB radios and things like that, right? They're great connectors, don't get me wrong, I like these. I like these a lot better than the other ones that they used way back in the day with that looked like a relatively large BNC connector. What are they called? N connectors, I believe, if I remember correctly. So anyways, I'll plug this in, put that on, and we don't have anything now. I'll turn the brightness up. Oh, we do. It's a little bit too much vertical gain. Fancy. Okay, so let's adjust the time base here. This is not in its on. That would be calibrated, yes, but not. Kind of slow things down here. And I can adjust the focus just a touch. It's nice and sharp. Let's see if we can lock this with a trigger. We have no trigger. It is on internal, yes. External and line, so line, external, internal. So if I put that there and I move this around, it should freeze this and lock this so that we can see this. So if I move the trigger around, it should lock that. And it is not. That's free run there. And this should have found it. Should find it right around the center mark. So it doesn't have any trigger. So that can be kind of an issue if you want to lock onto signals. So a lot of people have asked me in the past, oh, Paul, can you explain the trigger system? Okay, so here's a very easy way of explaining a trigger system in an oscilloscope. You're standing on the side of a road and a car passes you at 200 miles an hour. So can you give me any details about that car that just passed? And you're like, well, it went too fast, I can't see it. It was a blur. Same kind of thing with an oscilloscope. Now picture yourself in a car traveling at 200 miles an hour beside that car at 200 miles an hour. You're moving at the same speed. You can look over at the car, you can see the driver, you can see if he's shaved in the morning, and you can tell if he's got a steering wheel cover on, and you can tell all this kind of stuff, right? Because you're right beside him. But you can see there still might be a bit of movement. You might speed up or slow down, so you're going to probably be doing this at 200 miles an hour. Until you have an arm that reaches over and clamps onto the other car. Now you're locked together. So when it locks onto that, it's like locking onto a signal. So right now, it's like this is a 200 mile an hour car, right? And we can't really tell what this is doing. We see a whole bunch of movement, right? So if I move the time base around, I can kind of catch up, right? I can make them kind of... So you see that? I'm kind of matching the speed. So right now I'm kind of pacing the car. You could look at it like that. It's not really the same thing, but you can kind of look at it like that, okay? So, and then what happens is if you can have a triggering section, it's like that arm reaching over and clamping onto the other car, some big metal arm clamp holding onto the other car. Now you're locked together. Now you can look at that waveform. That's what a triggering section in an oscilloscope does. It allows you to lock on to a very, very fast signal so you can actually see it. So that's kind of a different way of looking at the triggering section in an oscilloscope. All right. So we have no trigger, so we got to find out what's going on with that. Everything else seems to be, looking okay. So we do have horizontal. We can see that. We can move the horizontal around. So, and we do have horizontal gain. So, of course, this is going to be for an external input, right? So, and any sweet magnifier. We can play with this later and see if we can look at some faster signals. All right, so what we need to do now is get into this thing here. So I'll just unhook this. And I'll turn it off. So it's got a nice red graticule on it. See that? Graticule's nice and red. Most of them are white. It's kind of neat. So I'll turn this off. And I will wait for this to just discharge for a few moments, and I'll show you how to get inside this in just a moment. Getting into these scopes is relatively easy. As you can see, it's unplugged right now. So all you do is you stick a screwdriver in here and give it about a turn. And the same thing with this, and it releases the little lock. And all you do after that is put your hands on it like so. Just do that. And you're inside. So I'll just move this cover out of the way because chances are that will fall on the bench and make just a horrible racket. And that's the construction inside a typical Tektronix oscilloscope. Nothing but the best. That is top notch. And it's so nice and clean in here. So obviously the previous owner of this took a lot of pride in the scope. It's spotless on this side. Now, another reason that this could be spotless too is that there is no, it's not forced air like a lot of them are. So many of the Tek scopes have forced air. They have a fan in the back and they're just, continually, blowing air through the scope, right? So this is pretty good. Even though they have filters, they still get, fine dust and stuff inside them. So this is looking spotless. So actually kind of surprised. It looks like there's paint overspray on the top though, on the cover. So somebody did get some white paint on it. You can see that here. See this? Some white overspray on this. So it's obviously been sitting in somebody's garage or something and they've been doing some painting. So I'll move this and this one here, and we're on the tube side now. And look at that. Thing looks like it rolled off the factory floor. Here, let's move this out of the way again. When those things fall, they make an incredible racket, those lids. Yeah, look at this. It looks just absolutely fantastic in here. Obviously, the previous owner cleaned this thing out with a toothbrush or something. Wow. Transistors under here, some tubes in here, and lots of tubes all over the place here. So you can see this. Yeah, tubes all over the top here and in the back. Typical television horizontal deflection tube back there. So not a whole lot of tubes, but enough. That's for sure. Some filter caps down here, power transformer, and yeah, very nicely laid out. Lots of 6DJ8s by the looks of it on the top here. You can see that. All the audio guys are going, I want to go buy one of these things for 6DJ8s. Please don't do that. It's a fantastic piece of history, these things. And they're such a nice piece of test equipment. When they work, they're so beautiful. It's a wonderful piece of equipment to use, right? So all of these Tek scopes are. So anyways, what I need to do now is get a manual and locate the triggering section in this. So I'll locate the triggering section and we'll test that out and see why we don't have trigger over here. So we need to match the speed of those two cars. Here's the instruction manual for this Tek Type 503. This really is an everything manual. It has schematics in here. It has a calibration procedure in here. It has everything. This is designed to help you get your scope working if something is wrong, and of course calibrate it if it's not up to spec. And that's the way they did things way back when. Oh, I forgot to show you this. So if that's not neat, check this out. For all of you that are new to tech equipment, see this right here, down in here? That's a roll of solder. That's how they encourage you to fix your equipment way back when. They include a roll of solder in your equipment so you can get it going again. Now granted, this is a special solder because of these little ceramic tie points here. These ceramic tie points have these little horseshoes in them, and if you don't use the correct solder, these little horseshoes will let go due to migration. So they provide a little roll of solder to make sure that you take proper care of your oscilloscope. It's better for them to include just a little bit of this solder than for you to hurt your own equipment, right? That's a company that cares about its customers, right there. So do you think if you bought a brand new computer today, they would include a roll of solder with your switch mode power supply? Maybe a couple of caps that don't develop ESR overnight? So anyways, how far we've come, right? Or maybe how far we've gone. So anyways, what we need to do here is, see how it has little tabs here? It says sweep trigger. So you want to open it to this page, and immediately we come to the triggering section, and it looks like somebody's already written in here. Now this isn't the book for that particular scope. I have quite a library of these books. So somebody has obviously worked on the triggering section in one of these scopes, and they've written down a whole bunch of things. It looks like it's a 70 volts peak to peak here, and looks like they've got plate voltages and cathode voltages and so on and so forth. So this is how we set everything up to test the trigger section here. So I'll just set that up. This is a bunch of flicking some switches here. Okay, so let's move this up here so you can see what I'm doing. Okay, so we did have the source on internal, so it says here, you can see this here, sweep normal. It says horizontal position centered, trigger source line here. And this is a sweep time 1 millisecond, trigger coupling, AC, and slope positive. So we have the sweep here, 1 millisecond. We need to put the source at line. All right, so basically it's going to be triggering on an AC signal from inside. Horizontal position is pretty much centered. And the magnifier is not on. What else? We have these set in the right position. I think we're ready to go. Yeah, we're pretty much ready to go. Okay, so you can see in the triggering section here, we have a bunch of 6DJ8s. So I think this is going to be very easy to find. So the audio tube of choice, let's zoom on into this here again. You can see 6DJ8, V24, and it says here V45A, V45B. So yeah, it looks like we're probably going to be on that row. And it's right behind the triggering section, so call me crazy, but I think that's probably the triggering section. So in order to start troubleshooting this, in order to troubleshoot this with style, what we need to do is use another piece of tech gear to do that. So, see the lights dim? Draws a little bit of current. Might possibly heat the house during the winter. So what I need to do is let this warm up. We'll use this plug-in here, one of my favorite plug-ins, the 1A2, aside from my very favoriteest plug-in, the 1A7A. And we'll start troubleshooting this scope over here. So I just need to let this warm up for about 5 minutes. It'll take about a minute and a bit for the trace to come on the screen just alone, so I'll let everything stabilize and I'll be right back. Okay, so here we are ready to go. So what we need to do is look for this, and that is here. And that is attached to pin 6 of the vacuum tube, so we should get this on the scope screen. All right, so off the plate of V24 pin 6. So this here is V24. So if we look a little closer, So if I move myself over here, we have 9, 8, 7, and 6. So that's this wire right here. So I need to clip the scope probe onto this. Okay, so I'll clip the ground here. And I will clip the scope probe onto this. And take a look at this. That looks pretty close. And the amplitude is pretty close as well. All right, so we're doing pretty good there. All right, so I'll remove the scope probe. You can see here, it goes away, right? So nicely that locks onto that. That's how this scope should work. All right, so we know that's working. So now, remove this. And I'll move this. Actually, I'll just remove that completely for a moment so it doesn't unclip and fly into the circuitry, because it probably would. So the next thing we need to look at is this here. We want to see if we have a square wave over here. So we should see a line, a line, a line, and a line, because you won't see this is, you know, pretty fast wave. So we'll just see top and bottom lines when we look at it. So we want to look at pin number 1 of V45B, and that's the next tube over. So that's this tube right here. So if we look here, this is the index. Is that the index? Where is the index? Let me see where the index is. This is the index right here. And this line right here is pin 1. This one right here. So what it is, I will attach probe again here. And we will clip on to 1. Let's take a look at what we have on the scope. And it looks like our triggering section is working. All right, so right now we're at, it says 2 volts, but we have a times 10 probe, so that's 20 volts per division. And so you're roughly about 30 volts. And it looks like what they have written down here is from 240 to 264. So we're just about 25 volts, right? So it's very close. See that? You can see that from 240 to 264, right? So we're just about 25 volts there. So we're very close, and we have our square. All right, so it looks like the triggering section is working on this. So what we should do is check the power supply and see how that is happening. So I'll just move some stuff around here, move this off to the side. I'll get this open to the power supply, and we'll start checking that. All right, you're in for a special treat with this. This is the power supply here. This is a vacuum tube switch mode power supply. Ever seen one of those before? So in a large switch mode power supply, say for your computer, you have a FET which drives the switching transformer. Well, in this case, that's this very large tube in here, and it drives this transformer. So we have an oscillator in the bottom, and this is our feedback right here, which sets the negative 100 volt supply. It's right off the negative 100 volt line. So that's a very important supply to have working. We have another regulator up here, which is a shunt regulator, and this makes no sense because there is no lead off. There should be an arrow pointing out from here because this is a shunt regulator. Now, I don't know if this is an earlier or a later schematic. I'll have to go and see if I can dig up another schematic and see if they've amended that, because you see how we have arrows coming off here? We should have 85 volts at this point here. That's the reason they have this resistor here. And we should have, you know, a line with an arrow that says 85 here. So, yeah, that's kind of odd because this wouldn't do anything just the way this is, right? You know, the only thing it could possibly ever do is load this down just a little bit, but that makes no sense to have a regulator to do that. So, interesting. Possibly Monday morning, no coffee with the engineer, and then somebody overlooked this. Obviously, the person that double checks everything hadn't had their coffee either. So we have a negative 3,000 volt supply here. And so just so you know, right, these scopes have got lots of voltage in them. So that's for the CRT. So we need to check all of this stuff. Not really this, we don't really need to worry about that because the CRT is glowing. If the CRT is glowing, chances are we're doing good there. So let's check this supply right here. It says positive 250, so we need to get to the top of R659, and the easiest way to do that is to spot the tube, look for pin 1 or 5, and then follow the resistor back. So you want to read on each side of this resistor. So at this side of the resistor, we should have about 85 volts. What it's doing here is it's not shown. And at the top here, we should have about 250. Okay, and usually they're pretty accurate. It just says 297. So interesting. All right, so very, very interesting. So what we'll do is we'll take a look here inside the scope. So this here on the other side is the 100 volt adjust right here. And if we look down, you can see just the camera angle right there. It is the 50, where is it? 5651. See that right there? And you can see they got pin 1 and 5 joined. All right, and that travels up through this, right up to this resistor here, and this is a different valued resistor, so there must be a multiple schematic for this. So at this point, we should have about 85 volts, about, and then we should have our 250 at this side, right? That would make sense, right? So I'll probe the this side right here first. All right, so I'll focus you in on the meter at the top here. Off to an angle just a little bit here. Move the camera over just to make that a little easier to see. Of course, now we have a shadow in there of some sort. Okay, so this is the 85 volt side, and we have 84.1.2. That's close enough. And on the other side, we have 275 volts. Well, 276 roughly, all right? Okay, so we know that that's somewhat within spec, right? So we know just by the fact that we have this, the scope screen is glowing, so we know that this is obviously working. If this T620 wasn't oscillating, we wouldn't have anything on the scope screen. So this should oscillate around 25 kilohertz, something like that. So in fact, we can probably see that on the scope here. Let's attach the scope. So what we can do is that signal, the drive signal, would be available at pin 4, which is the control grid. Right? Is that the control grid there? No, it's not. This is the control grid here, pin 5. So we should have a signal available there. So that would be, yeah, pin 5. Okay, so if I click this on here and go to, and where are we here? 1, 2, 3, 4, 5. And we take a look at the scope screen. Just adjust this. Get rid of this light on the top. There we have it. That's our relatively fast oscillation right there. So it is oscillating. Right? That should be around 25 to 30 kilohertz in that area somewhere, without any doing really precise math on that. So not bad. So it is working. We obviously know that because the CRT screen is glowing, right? If it wasn't glowing, then we would know that we wouldn't have anything there. Okay, so we know that that's happening. Let's see, what else have we got? We've got the positive 100 volt supply and the negative 100 volt supply. So the negative 100 volts is what controls all of this. So why don't we just check that out? All right, I found another schematic, and look. Positive 85 volts. So somebody didn't have their morning coffee in this manual here. I'm surprised that slipped by. Oh well, it happens to all of us. So there we go, they caught it. So this is 51K. And that makes sense to what's in this. So obviously this schematic is more relevant for this scope here, because that was the resistor that we read across here, was 51K, right? This one right here. Let's move this out of the way. This one right here. Grab my pointer. This one here. This was 51K, so 5-1, and then 3 zeros, 51K. Right there. So I guess that is more relevant. So this must be a very early book or something like that. So we need to test the negative 100 volt supply, and that's what this adjustment here is for again. That's the negative 100 volt supply there. And if I zoom on in, we can test that right at this point right here. Okay, my finger's a long ways away from that. Believe me, I'm nowhere near close to this. This right here, high voltage rectifier on the bottom. So I'm very far away from that. So this right here is our negative 100 volt supply. So what I will do is I will touch my probe to this, and I'll move you up to the voltmeter right here. So you see that off to the side. All right, there we go. It's negative 79 volts, so that's low. That has to be right at 100. So that's what sets everything in here. Kind of like the master supply. So this voltage has to be spot on. So that tells us that we have an issue. So maybe the 100 supply is just low. Wouldn't that be something? So let's take a look back down here at the scope. So that is the adjustment right there. So if I turn you around here, I'll disconnect that clip from the meter, turn this all around, and you can see what's going on in the backside here. So that's the really big FET if this was a switch mode power supply. That's what's oscillating there. That transformer, and you can see negative 100 volt adjust right there. See that written right down in there. So I will put a screwdriver in this and turn this as we take a look at the meter. So I'll move this around here. All right, proper clip found, and I'm about to adjust this right here. So move this around just a little bit. So let's see what we get on the meter. So this should very easily come to 100 volts if everything is working okay, because that's how these scopes work. So I'll move this one way. Nothing's happening. Well, there's absolutely nothing happening there. Yeah, absolutely nothing happening. Right? That was moved from side to side completely. So if I can get this all in. You see this here? Put this in here again. All right. So we definitely have a problem in that supply. Something is going on in there. So the very first thing that I would suspect would be capacitors. I would suspect that at first. So I'll zoom you into this here so I don't get too incredibly close. So what we want to do on the negative 100 volt supply is probe that, and we should have nice clean DC at this point. So let's check that out, see if these are okay. We can very quickly check to see if these are okay just by doing that, right? So easier than unhooking everything, right? So I'll move this back around again. And I'll get rid of the voltmeter. So I will attach the probe into the supply down at the bottom there. Okay, so I'll just ground this to the case like so, and we'll go right here. This is where that cap is. It's where the supply is anyways. Take a look at the scope screen. Whoa! Okay, well, what does this tell us? Easiest way to check a cap. Look at that. So I'll zoom on into this here. Move this forward so you don't have to see the glare of this lamp. So there we go. We definitely have an issue there. Look at that. Give it a bit more intensity. What does that mean? Well, that means we have no filtering. So that's what's wrong with the negative 100 volt supply. Let me get a capacitor and just clip it in there. So obviously that cap's open, or they're both open, one or the other. The place I was probing is right here on the diode, which is right here. So we should have 20 microfarad right about at this point right here. So what I'm going to do is, just for the test, I'm going to bridge in a capacitor here. You can see how the positive portion of the cap goes to the chassis because this is a negative supply. Alright, so what I'm going to do is take a 22 mic 450 volt cap right here. I'll take the positive, which will make the red lead of this cap here, and just attach it to the chassis. Any old place for now is fine. It's crude, but you know, it'll work. And then we'll take the negative cap and clip it to this diode. Okay, the scope is off right now, just so you know. So I don't want to be clipping anything in while it's on, right? Because it would instantly try to charge that cap and it could damage some circuitry in here. So everything is off. So I got the cap attached here. Can you see that? Where are they? Okay, so I'll set this off to the side so that it doesn't get in the way of anything. I'll turn the scope back on. Here we go. Let that warm up for just a moment. And let's see if I can get some stuff ready here while we're waiting. So I still have the ground attached here from the meter. And we'll turn some stuff up. Notice the screen has moved a little bit. Alright, so let's measure the voltage at the same spot again. So that's right at the actual voltage that we could read would be here. That's on the other side, but let's just read this. We should have a nice clean 100 volt negative supply if it's working, or somewhere around that. Oh, look at this. We got negative 94 volts now. I think we're on to something, huh? We're at negative 94 volts. That is a good sign. All right, I'll move this around very carefully because that cap is just loosely clipped in there, and I got ground leads and everything all over the place. Turn this around. Okay, I'll put my screwdriver back in here again. See if I can keep moving this without anything bad happening. I think I'm getting to my limit to where I'm going to start pulling leads off. All right, I'll poke the screwdriver into the negative 100 volt supply and move it around. Look at that. We've got a negative 100 volt supply. Leave it right there. It's about as close as we need to be, right? So it's definitely a cap. So what I need to do now is I'll just shut this all off. Just shut that all off. Move this back around over here again so I can do this safely without having wires short out and create more problems. So obviously the cap under here is bad. So there's a cap under here that has gone bad. So I will desolder that capacitor and we'll check its rating, and then we'll look at the other one as well, because there's two of them here. So there is this one here, 2 times 10 and 2 times 40. So we should have 20 mics and 80 mics right about here. So this is the one that was bad right after the diode. That's where we checked and we had that incredible amount of ripple there. So what I will do is, yeah, I'll just disconnect those capacitors and I'll be right back. We'll take some readings. Both the capacitors are now disconnected. Both C684 and 6C82 right here and here. So you can see I've opened this one lead right down here. Again, everything is safely discharged. See, I've opened this lead down here, and that attaches to the case of the capacitor, but the case is isolated, which allows me to use this as its own standoff, which will be really nice for a capacitor replacement. So this is isolated right now, and C684 up here is also open. You can see this down in here. I've opened this up down here so that we can test both of these capacitors without the circuit loading them down. So capacitor meter right over here. I will attach, because the positive of the cap down here is attached to the chassis, we'll attach the positive to the chassis, and we will go to the case here with a negative. 6 nanofarad. I'd say that capacitor is open. Yep, very bad. The capacitor is supposed to be 20 microfarad. That's really bad. Okay, so now over here, same deal. So what I'll do is I will attach the positive to this here, right? This is open from here, so I'll attach the positive here. And I will attach the negative to the negative of the cap. And what do we have here? 95, 96, and that should be about 80. Now these caps are very good capacitors. Very rarely do I ever see these fail at Tech. So these might actually be overachievers. We might actually have a little bit more than 40 microfarad per side. So there is quite a tolerance for these caps. One way to tell if it's leaking or not is to take the leakage tester. Will I trust this capacitor here still, even though it reads 96? Let's find out. I'll grab the leakage tester here and attach this into circuit. So this here and here. Okay. So there we go. All right, you ready? Let's go. Shut this light off so you can actually see what's going on. So we're on the red scale right now. See that? This should move down quickly if it's good, and it is. Look at that. Will I trust this capacitor after it's been tested with this? Absolutely. This is a very stingy tester. If this tells you your caps are good and there's no leakage, there really is none. So that's doing very good. So no leakage in this. So this can be left alone. So what I'm going to do is replace this capacitor down here. And after that's replaced, I will show you how I've installed a brand new capacitor, and we'll try out the scope and see what it looks like. See if we can get the thing to basically lock onto a signal. See if the triggering section works. The new capacitor is installed right here. So the old capacitor is out of circuit. It's still in the chassis, and it has a ground connection to it, which I'm using. So it's actually acting as a standoff for this capacitor, and this one is tied into circuit. So it's tied to this point right here and to ground. So that worked out really nice. So it's a must whenever you're replacing these old capacitors to completely remove them if they've failed, because it may be open now, but it could short later on. So we were testing the voltage at this point earlier to see if we could get any change. So now that everything is all done, we want to get really accurate and make sure that we definitely have the 100 volts. So we're going to tie in at this point right here, right? Because this is going to obviously be just a little bit of change across this. So we're going to tie in right here for the final adjustment, and we should get around negative 100 volts. That will be right at this point right here. So if I point to it, it's right here is where I'm tying in. All right, so I'll tie this in right here. If I can get a good connection with this. Let's try this again. All right, so we have negative 99.5 volts. That's pretty close. So what I'm going to do is carefully turn this and put the screwdriver back into over here. You can see where the adjustment is down in here. And I will adjust that for negative 100 volts right there. There it is. So now it'll be interesting to see how close the other voltages are. So I'll disconnect this out of here. Get rid of this probe. Put something a little bit more pokey in here, like this. Probe Master probe, by the way. Absolutely fantastic probes. So I've had these for so many years and they just hold up. Wires never break, nothing ever happens. Oh, I should mention, by the way, this tester that you saw is on Patreon. I designed and created this. If you want to build this, it's up there with all the plans, this leakage tester. All right. Okay, so let's take a look at the 250 volts again. So let's take a look at this and see how accurate we are. 250 at this point right here. So that, if I remember correctly, that was right here. See, look at how much closer that is, right? So we're only within 4 volts there. And on the other side, let's see what this is at. 84 again, no problems. So you can see that went way down. So, you know, 254 is absolutely fine for there. So this sets everything right, or this, this right here, this negative 100 volt supply. Can't see what I'm doing. Negative 100 volt supply here is setting everything, and that's this adjustment here is what we're adjusting. So that's what it needed. It looks like that cap is happy. Look at that. Solid. Negative 100.0, just doesn't move. Old Tektronix regulated supplies, they're fantastic. Probably stay like that throughout its entire temperature range as well. Oh, and if you want to take a look and see what this looks like on this scope now, remember where we tied in, we had that horrible looking wave there because of that cap. So I'll move you down here. Pardon the camera movement. Lots of movement here. Get rid of that. I'll tie in. You'll see a jump in the screen here because this is AC coupled. Okay, and I'll tie right into that point. That's what you see. That's what it should look like. That's DC. So if I move that over here, again, you can see I'm tied right in to the same point, right off that diode. So you can see how much ripple there is with just that cap open. That would obviously affect a lot. This cap is really good. And to be honest with you, most of these old tech scopes, I have so many of these, as you know, and so rarely do these electrolytics fail. Really, they hardly fail. I'm going to say, out of all the scopes I've seen, all of the tech scopes I've seen, that might be the second one that I've ever seen that's gone bad. All the rest of them, they just hold up. All the ones in the 555 scopes, the 547s, 535s, 545s, I've never seen one open or even short. They always just keep going and going and going. So very, very good capacitors in these. Again, Tektronix only bought the absolute best way back when and put them in these scopes. And of course, knowing where most of the other scopes went, like the 555 that I have is an old scope from Boeing. And I have some that were used in some pretty interesting places, let's put it that way. They came from some very interesting places. So hey, let's see if we can get a lock on this. Let's move this down here. Sorry for the camera movement here. It's just this tripod is rather rigid. Okay, so we have this now. Let's see if we can get a lock. I'll put that same signal in here. The signal generator's still on. All my cables are all tied up here, and I've got so many wires on this bench right now. So I'll back this out. You can see what I'm doing. Turn this down. Put this in here. Turn the intensity up. We'll put this on internal, and look at that. Locks like a champ. Isn't that nice? Don't even have to touch the control at all, just like the other scope. That's the nice thing about these tech scopes, right? Is they just work like a champ. Let's see if we can get this out of here, get a little bit of glare off the screen. And turn this up maybe. It's very bright. So there we have it. No problems there whatsoever. Very impressive. I wonder how well this is in alignment. I wonder how well it does. So we can magnify this. So for the fun of it, you know what? Let's put a 450. Actually, let's put a 1 megahertz signal into this. Here it is displaying 1 megahertz. Of course, we have it at ×2. Sweep time maxed out. That's it. And ×5. You can really expand upon that. We're also at maximum intensity to do that. So let's go 1.5 megahertz. Let's have some fun here. 1.5 megahertz. Is it still going to show us anything? 1.5. Let's try 2 megahertz. 2 megahertz. I'm turning the gain up as you see here. So it'll trigger at 2. Very touchy trigger. Maybe a little bit more gain. So the more gain we have, the easier it's going to trigger, right? So it's seeing 2. Of course, it's having an issue here at 2 megahertz. So this is with no magnifier. It still shows us a wave, but it's getting pretty tight. So that's ×2. And see if I can adjust the trigger here to steady that up a little. And it's looking like 2 megahertz is pushing like it was supposed to top out at 450, right? So we're really pushing this here. And that's that. Maximum sensitivity. So 2 megahertz. So the 503 will see 2 megahertz. Just like that. Let's go 2.5 megahertz. Wishful thinking. So if we go back to 450 kilohertz. There we go. Now the scope is happy. And there we go. Our position up. And now the vertical section can deal with it and everything. Let's get rid of the magnifier. Not bad, not bad at all. What we can do is we can test this and see how accurate it still is. Time-base wise. So let's just do that. So I don't know if I'm going to get into checking the, the vertical sensitivity and the gain and all that stuff, but let's just, for the fun of it, let's see if the time base is on. It should be kind of interesting. I'll set that up and I'll be right back. All right, place your bets. How accurate do you think this is going to be? So I've got the level set to auto right now, and if we take a look up top, I have the TU50 test unit. This is a unit designed to calibrate Tektronix oscilloscopes. This is on and warmed up at the top. So I'll click on 1000 microseconds, which is 1 millisecond. What do you think the scope is going to display? Do you think it's going to be accurate? Look at that. The 503 is spot on. Now, if this was decalibrated or something like that, say it was screwdrivered, you might have something like this. So the comb should be perfectly in line with the graticule, right? And if we click to the calibrated mode, that's calibrated right where it's supposed to be. Pretty amazing. So let's go here. And we'll go here. And make sure everything is aligned. Look at that. This is just spot on. The scope is doing just fine. No problems at all. So let's go down to here. Look at this, right down into here, right down into the microseconds, right? So we're at 5 microseconds right now. No problems. It's right on the line. So try and make it look as aligned on the camera as possible. It depends on what angle you look at the graticule from. So if the camera's kind of off to the side a bit, so you know, to my eye, I need to move this over just a little bit, but you can see it perfectly aligns with the graticule. So the comb is right there. This is, time base is in perfect alignment in this, and there's a lot of things that can throw that off. So this scope is doing very, very well. So it looks really like just the 100 volt supply, the negative 100 volt supply failed inside this. I'm pretty sure probably all the rest of it is spot on as well. And of course, you know, I'll end up off camera going through the entire thing and making sure that, you know, the vertical sensitivity is right and all of that, so everything matches up. But there you have it, scope repaired and time base accurate, and it will see about 2 megahertz before it really starts to not see anything anymore. Of course, it's well out of its calibrated zone, but you know, it still sees it. It could be used very comfortably for servicing AM radios and all that kind of stuff. So there you go. Little Tech 503 lives again. Seems like a happy little oscilloscope. Thanks for stopping by the lab today. Hope you enjoyed this video involving the Tech 503. Sure was a lot of fun getting it working again, and I really hope you enjoyed the process as much as I did. If you are enjoying these videos, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the very near future. We'll be taking a look at modern electronic devices and older electronic devices alike. So this channel is all about electronics, so we're going to be doing a lot of troubleshooting, a lot of repairs, a lot of circuitry design, restorations, teardowns, all of that stuff surrounding electronics. So if you're all about electronics, like I'm all about electronics, you're definitely going to want to subscribe and tap the bell symbol. That way you'll be notified as soon as I post a brand new video. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way and gaining access to many of my personal electronic inventions and designs, you're definitely going to want to check out my ongoing electronics course on Patreon. There's something there for everybody. If you're into modern electronics or antique electronics, I try to teach everything up there and try to convey as much information as I can. The goal of this whole thing is to take what I know and hand it over to you. That's why I'm doing this, and that's why I have that electronics course there. Definitely check it out. You'll enjoy it. I'll put the link just below the video's description under the Show More tab, and I'll pin the link at the top of the comments section. So if you click the link, it'll take you right there. All right, until next time, take care. Bye for now.